Okay, in this video we're going to be continuing in chapter 21. We're at what are the three important aspects of the adaptive immune response. Remember that one of the other names for the adaptive immune system is the specific immune system. I tend to call it the specific immune system because that's what I was taught back in the day. I also like that it's called specific because what it tells you is you have a specific army of cells that will fight E. coli differently from how you will fight Salmonella. Salmonella has its own specific army. So you have specific armies to fight specific pathogens. That's what the term specific essentially is going to mean for you here. All right. I have a note that says hyperlink. I'm really not sure where I meant for that. Maybe it went with the fever stuff from before. Okay, so first important aspect relating to the adaptive immune system is that specificity that I was talking about just a second ago. I do want you to think of everything here like it's puzzle pieces because shape is going to matter. The shape of these things that are called epitopes or antigenic determinants is going to determine whether or not you are able to mount an immune response against a particular antigen. If you don't have puzzle pieces that match up to the antigen's receptors, you are not going to be able to fight that particular antigen. So it's all about shapes here, and we need the pieces to be able to interlock. Second important thing, where the non-specific immune system was trying to keep everything localized and prevent it from spreading, here in the adaptive immune response, we do want everything to be systemic and body-wide, because if you get E. coli, it's not going to stay in one place, more than likely. It's going to get to a lot of different places, and we want to be able to fight it no matter where it is. And then, arguably the most important, we have memory cells, both B cells and T cells, that can live for a very long time. And that memory is a hugely important aspect of this system, because once you fight E. coli, you remember how to fight it, and you are better at fighting it in the future. In fact, you are so much better that anytime you fight it, you don't even know that you're fighting it because you wipe it out so fast that you don't even develop symptoms. So that memory is a very important factor here. Okay, next I gave you a little table. So remember that there's two branches to the specific immune response, your humoral immune system and then your cellular or cell-mediated immune system. Your humoral immune system is mediated by B cells or B lymphocytes, while your cellular is more about T lymphocytes. Anytime you see humor means body fluids. That's extracellular fluid, that can be lymph, that can be in the plasma, that can just be in the interstitial fluid in between your cells. While cellular is within solid tissues, like it's in the liver or it's in the spleen. The B cells that you have that are going to be protecting you with humoral immunity, they are going to differentiate into a specific kind of cell called a plasma cell. Those plasma cells, I like to consider them snipers, and the bullets that they shoot are called antibodies. Cellular immunity, on the other hand, is more like an active assassin. And the T cell is going to come around and it's going to poison whatever the bad guy is. So instead of firing bullets, we're going to dump poisons on things to kill things. So we're working with different armies, and we're killing in different ways, and we're killing in different locations. So that's why we have two different branches of your specific immune system. Okay, so I've been throwing that word antigen around. The way that your body views it is an antigen is not you. It is a foreign substance. And if it's foreign, we must murder it, essentially. So an antigen is essentially a bad guy. Complete antigens show both immunogenicity and reactivity. We're going to define both of those words next. Immunogenicity means that you are capable of creating an army to help fight whatever that antigen happens to be. Creating an army means that you can proliferate the T cells and or the B cells that are going to help you fight whatever that antigen happens to be. Now, immunogenicity is genetically determined. So there are some things that you will never be immunogenic to. There are other things that you are immunogenic to. It just depends on what you have the genes to be able to fight. Reactivity is more of an inflammation sort of a response. It means it will upset your immune system, but not necessarily that you will be able to make an army to fight it. You will end up, if something is reactive but not immunogenic, you will have an immune response to it, but you will never actually be immune to something. So the scenario that I'm giving you here, hopefully you all recognize that plant and you would know better than to touch that plant. That is poison ivy, which incidentally is the same thing as poison oak, just in case you didn't know that. It's the same species, Toxicodendron radicans. It produces this oil called urushiol. A lot of people, but not all people, are allergic to urushiol. For those people who are allergic, what that means is they are reactive to urushiol, but they are not immunogenic to it. Other people are not reactive to it, nor are they immunogenic to it. So they could go and just roll around in poison ivy and it wouldn't mean anything to them. But for those people who are reactive, it's going to promote a rash because their cells are going to degranulate, they're going to produce histamine. We're going to have some major problems that go along with that. We would need to treat that with steroids, but if they were to go and touch poison ivy again after a couple of weeks, once their rash went away, they would still break out in a rash again. In fact, if something is reactive, it tends to get worse the more you get exposed to it, not better, which that's something we're going to come back to when we talk about allergies a little bit later on. So one of the things that is mentioned on here is antigens can either be complete or incomplete. If they're complete, you can be immune to them. If they're incomplete, they're going to be annoyances that you will never be immune to. Antigenic determinants are also called epitopes. And again, I was taught epitopes and I tend to throw that word out there more often. Earlier, I had alluded to puzzle pieces. These are the puzzle piece shapes on the surface of the cells that your body is going to be responding to, because as it turns out, usually your body doesn't really care about the whole cell. It cares about those shapes on the surface of those cells. And if you have antibodies that match those shapes, that means that you are reactive to it. If you can produce antibodies, it also means that you're going to be immunogenic to it. And so this would be a complete antigen in that case. Notice that some antigens, they will have multiple antigenic determinants. Some don't. It just kind of depends on the antigen. The more antigenic determinants that are present on an antigen, the stronger your immune response can be against it. So the better that kind of is for you in a lot of cases. Now, your body also does have to be able to recognize you. You have what are known as self-antigens. I'm going to be talking a lot about flagpole flags in this sort of situation. MHC proteins are the flagpole that allows you to fly the flag that is your self-antigen. MHC stands for Major Histocompatibility Complex. So histocompatibility, histo is tissue, compatibility means compatible, so tissue compatibility. Whenever a person's going in for an organ transplant, we want to make sure that the organ that we're giving them is as compatible as possible so that the risk of rejection is lower. That's where this name comes from. Major just means kind of important. So we look for that whenever we're doing organ transplants, which is something we're going to come back to a little bit later on. You have your own unique MHC proteins. They are not even the same as your parents'. They are similar to your parents', but they are not the same. If you happen to have an identical twin, that's the one time where they are identical, unless there's been a spontaneous mutation there. Now, we've already talked about one example of an MHC protein, and that was the ABO blood typing stuff. So that's why I have that picture up there. Okay, skipping past the question slides. Okay, I do have the word immunocompetence on here. So if you have a lymphocyte that is immunocompetent, that means it knows who it is supposed to fight, and it is sort of primed and ready for that fight. The way that I like to try to describe that is it's been to boot camp. It kind of knows what it's supposed to be doing. However, it can still be naive. For example, I was in the Navy. I've been to boot camp. However, I have never once shot a person or actually been in a fight with a person. So I'm immunocompetent in that I have been to basic training and I have fired guns, but I am naive in that I have never actually been to war. So there's two separate terms that are sort of going to come back to us a little bit later on. Now, our cells are going to gain immunocompetence in different places. Our B cells do that in the bone marrow, while our T cells do that in the thymus gland. So that's, again, why they are named what they are named. Self-tolerance. Self-tolerance is critically important. We do not want a friendly fire situation that's happening here, because if we do get friendly fire, that's how you get autoimmune diseases. So we need your cells to recognize your cell flags and not attack your cell flags. So as they go through boot camp, they are supposed to learn what your self-antigens look like and learn, do not harm these cells. That's what self-tolerance means. If your B cells or T cells do not learn self-tolerance correctly, again, that's how you end up with an autoimmune disease. We've talked about several in the past. This is a creepy one that we had not talked about before. In this case, the immune system's attacking the eye, and it's creating these tumors in the eye. So this is what happens when you lose self-tolerance. What are the major types of antigen-presenting cells? So sort of like in past chapters, your book turns into an alphabet soup at this point, and we've got APCs and B cells and T cells and CD4 and CD8 and a whole slew of different strings of letters that come through here. APC is antigen presenting cell, and it's trying to tell you exactly in the name exactly what it's going to do. It's a cell that presents antigens. So in the scenario that I'm going to be giving you here, we've got a cell that I like to call mom, and I call it mom because mom tends to be able to fix whatever your problems happen to be. She can find stuff that needs to be found. She can help you with your homework. She can beat up your bully for you if you need that, whatever. Mom can fix your problems. So antigen presenting cells, they're going to run around and they are going to find antigens, and then they are going to come and they're going to tell mom, the helper T cell, that they have found an antigen. So any of your phagocytes are antigen-presenting cells. Macrophages happen to be one of the best at it, but that can also include neutrophils, eosinophils, basophils. Those would also count as antigen-presenting cells. Dendritic cells, we talked about those the first time last semester back in skin. Those are antigen-presenting cells that were found in the stratum spinosum moving around within the epidermis of the skin. Any of those cells that are running around looking for bad guys to eat, they are going to, after they eat the bad guy, they're going to run and go tell mom that they just ate a bad guy. Okay. Antigen challenge. I'm so easily amused. You'll have no idea. Okay, so antigen challenge is like this GIF. It is a come at me bro situation. Here's the thing that a lot of people don't understand. Your immune system is essentially just the laziest thing in the world, and it's just sitting there doing its thing, being lazy, until an antigen comes up and tries to pick a fight with it. The second an antigen tries to pick a fight with it, your immune system is like your drunk BFF who is always going to accept that fight every single time and without fail. It's going to assume it's going to win that fight every time, which it won't, but it's going to at least try to help you with that. So the antigen challenge is whatever the antigen happens to be, again, E. coli, COVID, does not matter. It's going to come up to a specific cell within your immune system, a B cell, a T cell, an antigen presenting cell, doesn't matter. And it's going to challenge that cell to a fight. Now, it's not really as cool as all of that. It just bumps up against it. And if it happens to bind to a receptor on that cell, your immune system is going to accept that challenge and the fight begins. If the cell that the antigen bumps up against does not have a puzzle piece shape that matches, your immune system is not going to accept that challenge. So ideally, whatever the antigen bumps up against is going to be ready for the fight, and it's going to accept the challenge. It really sucks when the antigen comes up and it starts bouncing against cells and none of the cells accept the challenge, because that means the antigen gets to live in you and divide in you and survive in you longer. And that means you have a better chance of getting sick and staying sick and showing symptoms that much longer. So the faster you can accept the challenge, the better. And that's going to play a role when we come back to those memory cells later on. Now, once you accept the antigen challenge, the cell that accepts the challenge, because it had the puzzle piece shape that matched, we're going to make a clone army just like in Star Wars. I don't know why I got sing-songy there. Again, I'm giddy. Apparently I need to eat something. Okay, so the cell that accepts the challenge is going to start to divide by mitosis over and over and over again. And again, that process is called proliferation. And I liken it to Star Wars because that was the whole clone army thing they had going on, which it's been way too long since I've watched it. But they just kept making a clone of one dude, and they had their clone army that made all the stormtroopers. It was all the same dude. At least in the original movies, it got weird at the end. All of those cells are all exactly like each other, and they are all primed to fight the antigen that picked the fight to begin with. So clonal selection makes your army. So once you accept the challenge and you do clonal selection, you now have an army that is going to fight the antigen. So why did my clicker not work? There we go. Here's the picture that shows you everything that we sort of just talked about from the book. So let's say that this antigen is E. coli. You just ate some spinach that was infected. contaminated would be the appropriate word there. So you ate a bunch of E. coli cells. Well, after you absorb this E. coli, it's going to start bumping into a bunch of cells, but only some of your cells can accept the challenge. It depends on which receptors they have. So it bumps into this cell. Well, this cell doesn't have the shapes that match. So this cell cannot accept the challenge. This cell does not have the shapes that match, so this cell cannot accept the challenge. So the antigen challenged all three of these cells, but only this cell in the middle actually accepted the challenge and then did the clonal selection proliferation thing and started to make the clone army. Divided by mitosis to make 2 cells, the 2 cells divided to make 4 cells, 4 made 8, and so on, and we keep dividing to make our clone army. Once we have our clone army, some of the cells are going to differentiate into plasma cells. And remember, the plasma cells are the snipers. The bullets they fire are antibodies. Antibodies are going to help wipe out the antigens by clumping them together, is essentially how antibodies are going to work. Some of the other cells that we create during proliferation are going to end up becoming memory cells. Memory cells, again, very long-lived. You keep a lot of them around in various places in your body so that if that same antigen comes back in 2 years, there's cells hanging out that are going to accept the antigen challenge faster than you did the first time around, so that you don't even get sick the second time around. And here's the book trying to show you that. So again, you ate now some peanut butter 2 years after you ate spinach. The peanut butter had that same stupid E. coli in it that made you sick 2 years ago, but this time you had memory cells that were hanging around and they remember the E. coli from 2 years ago. So not only did it not take as long to accept the antigen challenge, it doesn't take you as long to make your clone army. And when you make your clone army, you make it faster, stronger, and better. The plasma cells make more antibodies and you make even more memory cells. So your secondary response, it's faster, stronger, and better than the first response that you had. So getting some of those terms defined, we had already defined clonal selection. So next up, plasma cells, again, snipers. The bullets that they fire are antibodies. So this is one branch of your army and they're all snipers. There are also memory cells that you create. You have memory B cells and memory T cells that we're going to talk about later on. But for right now, memory B cells live a long time. They will accept antigen challenges faster in the future so that you have a stronger, faster secondary response. Contrast the primary immune response with the secondary immune response. So primary immune response is the first time that you ever meet a particular antigen. I think I mentioned the story the first time I recorded the non-specific challenge, but the first time that I made my son a chocolate silk pie, he got violently ill, more than likely from salmonella that was in the eggs from the chocolate silk pie. He ate some of the pie. Everybody else in the family ate some of the pie, but he got horrifically sick. That's because this was the first primary time he had been exposed to salmonella. So since he had never met it before, he had no memory cells. So salmonella bounced around for a while trying to challenge cells, but nobody accepted the challenge. The whole time it was bouncing around, it was making him sick, and he was projectile vomiting all over the house because toddlers don't understand how toilets work, apparently. And so he had all these symptoms the first time around. Once he did finally start to make his army, the army was relatively small, but it got the salmonella under control. Everybody else in the family, though, had met salmonella before, so we were all having a secondary response. Our secondary response was faster, stronger, and better. So we never developed symptoms. Our army was already there because the memory cells were already there. We made more B cells, plasma cells. We made more antibodies. So we didn't even have any symptoms that went along with that. That's the beauty of a secondary response. You get exposed to things all the time that you have no idea you're getting exposed to because your secondary response works exactly like it's supposed to. That's where I'm going to go ahead and stop this video. I'll pick up with vaccines in the next one.